Okay, this example is also going to be a rational function, but this example is going to be one that has a slant asymptote. So I've got an explanation here for you to have in your notes so that when you um, look at a rational function, like how do you know that it's going to have a slant asymptote? As it states, it says that the slant asymptote occurs if the degree of the numerator exceeds the degree of the denominator by 1, and it has to be exactly by 1. And then in order to find the slant asymptote, you're going to use long division to do that. Now, when the degree of your numerator is larger than the degree of your denominator, if you remember from the previous section, we had discussed that that actually meant that there was not a horizontal asymptote. So when you have a slant asymptote, you're not going to have a horizontal asymptote. But again, when the numerator has to exceed exactly by 1. All right, so here's the example that we're going to look at. Okay, so first of all, let's discuss the domain of this function. And of course, your domain is going to have to exclude positive 2 because positive 2 is going to make your denominator equal 0. Okay, so we need to keep that in mind as we go through. All right, your first derivative, and you're just going to have to use your quotient rule in order to find your first derivative, but that's going to end up being x squared minus 4x divided by x minus 2 squared. Okay, from here, locating the critical numbers, so we need to set our numerator equal to 0 and our denominator equal to 0. Now, solving the numerator, you're going to have to factor out an x. Therefore, you'll have x equals 0 and x equal 4. And then solving your expression from your denominator is going to give you x equal 2. Now, if you remember, 2 is what we excluded from the domain. So, technically, by definition, that's not actually a critical number, but we still use that whenever we do our sign graph. So this time I'll have 3 numbers that I need to put on my sign graph. So we'll have 0, 2, and 4. And then you need to pick a test number for each of these sections. So I'll go with -1, +1, 3, and 5. Now test numbers will be substituted back into your first derivative, and when you do that for each of these values, the -1 is going to give you a positive value, +1 will give you a negative value, +3 will give you a negative value, and +5 will give you a positive value. So this section's increasing, decreasing, decreasing, and increasing. All right, so let's go ahead and write the intervals for the increasing and decreasing. So increasing would be -infinity to 0, so that's this section. And then this section would be from 4 to infinity. And now our decreasing, now since these are side by side, can I put them all together in one interval? That's going to depend if this number here, the +2, separates it, is it in the domain? And if it's in the domain, then you can group it all together. But see, 2 is the number that we had to leave out of our domain, so we have to write this as 2 separate intervals. So we would have 0 to 2, and then from 2 to 4. All right, also from here is where we can determine our maxes and mins. Okay, so here my function's increasing and then decreasing, so this would be a maximum, and then decreasing and then increasing is going to give me a minimum. All right, so we need to locate those points. So f of 0, again, these are going to be plugged back into the original function this time. So if you substitute in 0, you're going to get -2. So the point 0, -2 is a max. and then substitute in the 4. Again, you're substituting these into the original function, so you'll get a value of 6, so that will be the 0.46, which is going to be a min. Okay, now from here, you're going to be ready to do your second derivative, which is going to require quotient rule again. Okay, so my second derivative, after you go through your quotient rule, will simplify to be this. Okay. Now, when I go to find out what values cause this to equal 0, this is actually not ever going to be equal to 0, because that's the part that comes from your numerator, and your numerator's locked in at 8. But I can find a value where it's going to be undefined, and that's going to be at x equal 2. So my sine graph with my second derivative, I will only have the positive 2 to put on that. All right, your test numbers, so I'm going to use 0 and 3. Again, you're going to substitute these test values into your second derivative. This is going to give you negative, and this will give you positive. So this portion's concave down, this portion's concave up. All right, so let's write those intervals. So concave up is from 2 to infinity, and concave down is going to be negative infinity to positive 2. Now, usually when you have a change in concavity, remember, is where you have a point of inflection, but my change in concavity is occurring at positive 2, and positive 2, remember, is not in the domain. So with my points of inflection, that's actually going to be none. Okay? All right, let's talk about asymptotes. So as far as a vertical asymptote, that's going to occur at the values that's going to cause your original function to be undefined, and that's going to be at positive 2. Okay. Now, when it comes to doing the horizontal asymptotes and the slant asymptote, remember, you've got to look at the degrees. Okay. So what we learned about the horizontal was if the degree of the numerator is greater than the degree of your denominator, that means that there's not going to be a horizontal. So no horizontal asymptote. Now the slant occurs when the degree of the top is exactly 1 more than the degree of the bottom, and that's what you have here because the top is 2 and the bottom's 1. So you do have a slant asymptote. Okay, so now let's work on finding this slant asymptote. So as I told you, what you're going to have to do is long division. Okay, so we're going to have the x minus 2 that we've got to divide into x squared minus 2x plus 4. All right, so I always look at it this way. What do I need to multiply the x by to get x squared? And that would be x. So now I put that on the top. What I put on the top, I have to multiply times both terms out front. So x times x is x squared. X times negative 2 is negative 2x. And then at this point, what you're going to do is subtract. So x squared minus x squared is 0, which you do want this to always be 0. But this one also happens to be 0. Because if you do negative 2 minus negative 2, therefore you get 0x. All right, bring down your plus 4. Now, what would you need to multiply the x by to get 0x? And that would have to just be 0. Of course, I know adding a 0 is not changing anything. I'm just carrying you through the whole process here. So 0 times x is 0x. 0 times negative 2 is 0. And then you're supposed to subtract. Of course, 0 minus 0 is 0. Again, that first column of subtraction is supposed to give you 0. But then you do 4 minus 0, and you get a remainder of 4. Now, your slant asymptote is going to be, it's a line, so therefore it's y equals. But actually your remainder is not going to affect your slant asymptote. It's going to be the expression that you have here on the top. Of course, x plus 0 is just x. So the line y equal x is going to be your slant asymptote. All right, let's talk about intercepts. So let's talk about the x-intercept. Now an x-intercept is going to occur where your function is equal to 0, which is going to come from the numerator. So you would have the x squared minus 2x plus 4 equals 0. Now that's not going to factor. You would have to use quadratic formula, but just to save time here, you're actually not going to get anything out of this, because when you use your quadratic formula, then what you're going to end up with is imaginary solutions. Okay? Now, just because you're using quadratic formula, are you guaranteed to get imaginary? No. Okay? But like I said, I just know you're not going to get anything out of it, so just saving time, nothing there. Okay, y-intercept. Of course, you find a y-intercept by substituting 0 in for x. So just plug the 0 back into the original function, and when you work that out, then you're going to end up getting y equal 4 over negative 2, of course, which gives us negative 2. So that's the point 0, negative 2. Okay, so that's all the information that we need. So now what we're ready to do is to actually graph this. Here's looking for my extra piece of paper. Okay, so to graph it, all right, what you're going to need to do, of course, is put in your asymptotes and put in your points that you have found. So I have a vertical asymptote at 2. Now my slant asymptote, remember, is the line y equal x. So, just graph that based on y-intercept and slope. So of course that's going to go through the origin, and it has a slope of 1. So up 1, right 1. I'll go ahead and count it off one more time. Up 1, right 1. So this is going to be my slant asymptote. Okay. Now the points that we found, we have a max at 0, negative 2. And at 4, 6. It's going to be a min. The 4, 6 is a min. This one's a max. Of course, there were no points of inflection. The y-intercept happened, of course, to also be the maximum value that we have here. So your graph, and you're going to stay between your asymptotes, comes up. Of course, this is a maximum point, so we know once it reaches there, it curves and it's got to come back down. Now, if you look at like your increasing and decreasing, like from negative infinity to 0 was a section that was increasing, and then from 0 to 2 was decreasing. And then if you look at concavity, this whole section from negative infinity to 2 was all supposed to be concave down. So you can just kind of check that and make sure everything's coordinating the way it's supposed to be. This section is going to look like this. This is a minimum value, so we know that that's the lowest that point's this part of the graph is going to be. And again, if you check increasing, decreasing, concavity, then you'll see that all of that matches up with what we determined on that.